Hello, everyone, and thank you for joining us today. Welcome to Megger's monthly Testing Tactics webinar series. Today's topic is tan delta testing on medium voltage cables. My name is Michael Fleischer, and I'm the Digital Marketing Specialist for Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you'll see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. All webinar attendees are eligible to receive one NITA CTD and one PDH or zero point 0.1 CEU for attending. You will receive this in an email within 2 business days of the webinar. That email will also include a copy of the PowerPoint presentation and a link to a video recording of the webinar if you'd like to watch it again or share it with your colleagues. Remember, you can ask questions at any time during the presentation, and they will be answered at the end of the webinar during the Q&A session. Our presenter today is Javier Ruiz, Cable Fault Location Test and Diagnostic Area Sales Manager. Also, to assist with the question and answer session, we will have 2 panelists joining us today. Robert Probst, Product Manager, and Henning Oetjen, Product Manager. All right, let's go ahead and get started. Thank you for joining us today, Javier.
Thank you very much, Michael, for the introduction, and thank you to everyone to attend to this webinar. So let's start with the agenda. First, we'll go through the basics. We will see the principal characteristics of medium voltage cables. Then we will continue with the failures mechanisms in medium voltage cables, and then we will do a brief review of the Vlf test, partial discharge, and tan delta test. Then we will continue with a more detailed review of the Vlf, and we will move on cable insulation engine process, and then we will start to see what is the tan delta, when and why do we use it. Then we will see what we can see and what we cannot see with the tan delta. That means the capabilities and limitations. And then we will move to how does it work, what are the parameters involved in the tan delta, the assessment criteria for the tan delta, and finally we will go to the how to interpret the results, how we do the tan delta test, and finally the tan delta equipment that we have in Megger. Okay, so talking of medium voltage cables, the typical voltage for medium voltage cables will go from 5 kV to 35 kV. We could say that the more typical voltage for medium voltage cables could be 15 kV, 25, and 35 kV. In terms of the insulation, we have what we call polymeric insulations, EPR and Xlpe, and we have also the paper impregnated lead cables. If you see in the first 3 pictures from the left of the slide, we can see the EPR, then we have the Xlpe, and then the paper impregnated lead cable. And all of them are in a configuration of 1 phase. The last 2 pictures in the right of the slide are a 3-phase configuration cable. Okay, so in terms of the failures mechanism for medium voltage cables, we should distinguish between local issues and global issues. Local issues, we will find them mainly in terminations and splices, and typically will be workmanship problems, but also would be manufacturer defects as well. And basically, those are single points that are an area of weakness of the cable. By the other hand, the global issue is a distributed wire trees in the entire length of the bulk insulation. In the case of Xlpe cables, in the case of paper impregnated cables, the global issue will be the cellulose degradation. So it's important that we distinguish between local issues and global issues. And depending on what kind of problems we are dealing with, we can use DLF or partial discharge to detect local issues, okay? in the case of the Vlf to convert in fault local issues, that problem should be a severe or a big problem. But if the local issue we are looking for is a small one, we will not convert in fault with the Vlf, and then maybe we should use partial discharge. If we are dealing with global issues, okay, for instance, in the Xlpe insulation wire threes, and then we will use the tan delta test. Okay, that is what we will discuss in detail in the next slides. So, doing a quick review of the Vlf test, we can say that the Vlf is a AC over voltage test. It's a go or no go test. That means that the cable will pass or will fail during the test, and the Vlf test will provide limited diagnostic information. Okay, we can use the Vlf test for installation, acceptance, or maintenance tests, and or after repairing a cable. And for the Vlf test, we have two wave shapes, the sinus wave shape and the cosinus rectangular wave shape. And the frequency that we will use in this AC high-pod test, it's 0.1 hertz. The reason, because I want to do a quick review of the Vlf test, is because for the tan delta test, we will see later that we will use the sinus wave shape for the tan delta. Okay, so let's start with the cable insulation aging process. Today, in the present, we could say that all medium voltage power cables have a high life expectancy. Okay, but during the whole service life, they are subject to thermal, electrical, mechanical, and environmental stresses. And these stresses will change the morphological properties of the insulation. In other words, will age or degrade the insulation material of the cable. So this will result in a decrease of the breakdown strength of the insulation, and the decrease of the insulation breakdown strength will finally lead to cable failures. And of course, to avoid failures in the insulation, the measurement of the dielectric losses could be a helpful tool. So, regarding the cable insulation aging process for paper impregnated PIL cables, the most important aging phenomenon for PIL cables is the degradation of the cellulose. What basically means that the moisture comes free from the paper insulation because of thermal or chemical processes. Of course, the corrosion of the outer sheath and the generation of holes in the lead sheath will lead to an increase of the moisture content. Okay, it's in the case of PIL cables. Regarding Xlpe cables or polymeric insulation, by far the wire threes are the most important aging phenomenon for polymer cables, and could lead into early cable faults. Okay, so to see the complete process of the aging, of the insulation aging for Xlpe cables, we could say that we will start with the ingress of water by diffusion or sheath faults. Then we will have the generation and growth of wire threes. This process will take at least 5 years. Okay, and then when the wire trees reaches a critical size, okay, maybe an overvoltage can create an electrical tree underneath of the wire tree, and we will start first with a partial discharge process, and then we will have an electrical tree. And once we have an electrical tree in the insulation of the cable, it will take hours, maximum a couple of days to have a fault. To illustrate this process, we have this picture, and all start with a sheath fault in the cable, and the wire surrounding the cable will ingress in the insulation of my cable, and then I will have the existence of wire trees, and the electrical field will do that we convert that wire tree in electrical tree. And once that we have the electrical tree, sooner or later we will have a breakdown of the cable. So continue with the insulation agent process in Xlpe cables. It's important to know that when the wire trees in the cable can easily be recognized by typical pinhole failures in the Xlpe insulation. For the reason, we recommend that if such fails occurs, to replace between 5 to 10 meters of cable, as the wire trees will spread out of a longer distance. So, what is the tan delta test? Okay, well, we can say that tan delta or tangent delta test is a global method of testing cables to determine the remaining life expectancy of the insulation. We know that there is a correlation between an increase of 0.1 hertz tangent delta and a decrease in insulation breakdown voltage level at power frequencies. That is something that we know. So the tan delta test is based on Vlf technology, is a diagnostic test that results in qualitative numbers, and we also can compare the values of the tan delta with the IEEE guide, and of course the tan delta is a prescribed test method by the IEEE 400.2. So when to use the tan delta? When to use the tan delta? Well, typically we will use the tan delta on aged cables, at least 5 years old. The idea is to detect the aging conditions in the insulation of the cable. We can use the tan delta as part of a cable maintenance strategy to alert critical aged cables before in-service faults and up to 1 or 2 years notice. And the idea is that if we have, for instance, a big populations of old cables and we want to start to replace them, but we have no idea where to start, then the tan delta test will be a very good tool to help us to target the worst cables first. And in this way, we will use in wisely way the money we have. So why to use the tan delta? Why to use the tan delta? Well, first, because it's a non-destructive test. It's very unlikely to fault the cable during or after the test. We will see later that the maximum voltage that we will apply during the tan delta test is 1.5 U0. So it's again very unlikely to fault the cable during or after the test. And it's a diagnostic tool to measure the remaining life of the cable. And the idea is to detect the aging conditions in the insulation of the cable. Of course, we use the tan delta to increase the system reliability. Okay, that is the reason because we use the tan delta. So, what are the capabilities and limitations of the tan delta test? What can it detect? Well, for sure, provides an overall condition assessment. We can estimate the life left in the cable, and we can detect presence of water trees. We can detect contaminants in the insulation, corroding metallic shields, insulation moisture, degraded accessories, oil leakage in the case of pill cables. And of course, we can assess effectiveness of repairs before and after the measurements. So what can it not detect? What we cannot see with the tan delta? Well, we cannot locate discrete problems. Only that there is or is not a problem. But for instance, if we have, let's say that we have a very high values or a very bad values of in a tan delta test, we could not say if the problem comes from a corroded concentric or from wire trees. Okay, that will be quite difficult to know only doing the tan delta test. Okay. Also, we cannot see problems in the jacket or the lead sheath, and of course, we cannot see poor workmanship or installation defects. And neither we can use the tan delta or we should use the tan delta in a single type of cable, because if we have mixed cable, well, different characteristics will mask the defects. How does it work? Well, let's use first some kind of theoretical approach. And for simplistic purposes, let's say that the circuit we are seeing right now is the equivalent circuit of a cable. Okay? So, in this circuit that modeled a cable, all the current, the total current, will be the current that will go through this resistor plus the current that will go through this capacitor. Okay, so the total current will be equal to the resistive current plus the capacitive current. Okay, well, let's consider that the resistor in my circuit is perfect. In other words, that the value of the resistance trends to infinite. This guy is a perfect resistor, so the value of the resistance trends to infinite. This will mean that all the current in my circuit or in my cable is a capacitive current, and then it is 90 degrees shifted to the voltage applied. That means that we will have, if we have a graphic of the voltage versus current, we will have something like this, okay? And we have the voltage, and we have the current, and we have an angle of 90 degrees, okay? Indicates that the resistive current is equal to 0. Now, let's consider that this resistor is no longer perfect, so the resistance no longer will trend to infinite. That means that we will start to see some current going through the resistor. We will see some resistive current going through the resistor. In this case, we will start to see a little component of the resistive current over here. And then the diagram that will be described, this situation will be this one, in which we have a little component of the resistive current over here, and this angle, the delta angle, will be a good indication of how good or how bad is the insulation in my cables. This angle is a good indicator. So if this angle trends to 90 degrees, that means that the insulation in my cable is aging. And if this angle trends to 0, that means that I have almost an perfect insulation. So the trigonometric function that correlates the resistive current and the capacitive one is the tan delta, and we can see here the function that correlates the resistive current and the capacitive one. This is one approach. There is another easy one, okay, a pragmatic approach, in which if we consider the equation that the voltage is equal to the current multiplied by the resistance, and if we consider that the water is less resistive than the insulation, that means that this guy will go down, and if the resistance goes down and the voltage stays the same, then the resistive current or losses goes up. And if the resistive current goes up, then the tan delta number gets bigger. Once again, if the resistance goes down, the voltage stays the same, then the resistive current will goes up. And if the resistive current goes up, then the tan delta goes up. And we can see very easy from this equation, one more time, if the resistive current goes up, the tan delta test will goes up. If the resistive current goes down, then the tan delta goes down. So, doing a summary of how the tan delta work, we can say that the tan delta is a scalar quantity, it's a dimensionless unit. We measure the angle or the ratio of the resistive to the capacitive current. As the cable age, the insulation resistance decrease, the resistive current increase, and the angle increases. And of course, we can compare this angle to the IEEE 400.2, and we'll be able to make an assessment, to make a decision. So, what are the parameters we will apply? Well, first of all, we will use a sinus wave shape. The test frequency must be 0.1 hertz. We will measure between 8 to 10 values of tan delta per voltage step, and we will apply 3 voltage steps. The first one will be 0.5 U0, the second one will be 1.0 U0, and the last one will be 1.5 U0. Why we need to use a sine wave shape? Why? Why not to use the cosinus rectangular wave shape? Well, if we remember the theoretical approach for explaining the tan delta, we say that in a purely capacitive circuit, the current leads the voltage by a 90-degree angle. We can see here the current, the blue trace, is leading the voltage by an angle of 90 degrees. Okay, we have here the angle. Okay, so this is very important to measure the tan delta. And the problem is that if we try to use a cosine rectangular wave shape to measure the tan delta, then we don't have a phase reference between current and voltage, because in the cosinus rectangular wave shape, we will have these DC plateaus or these DC components, okay? And that's the problem, because then, as I said, we don't have phase reference, okay, between the current and the voltage. That is the reason because we use the sinus wave shape to measure the tan delta. So, what parameters we will measure? The first one, it's the mean Vlf tan delta, or the mean value of the tan delta. And as we can see in the equation, the mean value of the tan delta is the summatory of all the individual tan delta values, okay, is the summatory of all the individual tan delta values divided by the number of values, in this case 30. Okay, so that means that the mean value of the tan delta is the summatory of all these tan delta values in each voltage step, and we will sum all them, and we will divide by the number, or the total number of measurements, in this case, once again, 30. The second parameter we will measure will be the differential Vlf tan delta, or tip up, and the tan, or also the delta of the tan delta. And the delta of the tan delta is the mean value of the tan delta at 1.5 U0, and we will subtract the mean value of the tan delta we get at 0.5 U0, as we can see in this equation. Okay, so we will get the mean value of the tan delta at 1.5, and we will subtract the mean value we got at 0.5. Okay, this is the second parameter we will measure. The third one and the last one will be the standard deviation of Vlf tan delta tan stability. Okay, and the standard deviation, what really means is how far or how close are each other the values of the tan delta for each voltage step. In the first, in this case, for 0.5 U naught, we can see that the standard deviation is very low because all the values are very close each other, are very close among them. But in 1 U naught, we can see that the standard deviation is high because the values are not are far one from other. Okay, and it's pretty much the same situation in 1.5 U naught. Okay, well, so the standard deviation is really an indication about the deviation of the tan delta values with a voltage step. Okay, and this will be the last one, the third one, measurement or parameter we will measure. So once we done with our tan delta test, we will compare our stability or tan delta, the delta of the tan delta and the mean value with a table. In this case, we are seeing the table number 4 for PE and Xlpe cables. And the condition assessment that we can get is no action required, further study advised, and action required. And that means that, for instance, no action required means that no indication of severe problem in the short term. That means that the cable system can be returned to service, and the cable system should be retested at some later date. Okay, maybe in 4 years we can do one more time the tan delta test if in the first measurement we get a no action required result. The next one is the further study advised, which means that additional information is needed to make an assessment. And maybe we can compare historical results of the tested cable system, or we can do additional diagnostic tests, for instance, a monitor with stand test, or maybe we can do an inspection, a visual analysis of the circuit components to look for splices with water or wet terminations. Okay? And the action required, the last result we can get, action required means that we have a really poor insulation condition and the cable system should be considered for replacement or repair immediately. Okay? Something that I would like to say is that if we do by the first time a tan delta test in an old cable and the result we got is action required, we will not recommend to replace the cable. Maybe we should do additional measurements or maybe do a visual analysis and maybe repeat the tan delta test in 1 year to see if we have variations of the values of the delta of the tan delta or the deviation, the standard deviation. Okay. So to continue with the assessment criteria, we can see that for Xlpe insulation, there is a voltage dependency. For instance, in this graphic, we can see that for a new cable or a reference cable, that is the red graphic that we have here, we have almost a flat line, okay, for a new cable. But if we see the blue one, that is the graphic for a strongly service-aged cable, we will see that we have an increase of the values of the tan delta as we increase the voltage. Okay, so that means that we have a voltage dependency of the tan delta of new and service-aged medium voltage Xlpe cables. And we have this situation also in paper impregnated lead cables. If you see this graphic, we can see that for well impregnated cables we have almost a flat line, but for a poorly impregnated we have an increase of the tan delta as we increase the voltage. Okay. How to interpret the results? Well, we will see some graphics of tan delta. The first one is this one, that is the tan delta on a good cable. If you see, the three phases are have pretty much the same graphic, the same behavior. In the next slide, we have the same cable, but we can see in the graphic of the left that the tan delta test was made during rain. Okay, so the values of the tan delta are higher in this test. But for the same cable, we did the tan delta on a sunny day, and we get a better result or lower values for the tan delta, which means that also the weather conditions could affect the results of the tan delta test. Okay, and this one is a really interesting graphic, because if you see the phase L3, you will see that we start with very high values of the tan delta, but as we increase the voltage, the tan delta decreases, which is not very is not common. It's a little strange for the tan delta, because we will expect that as we increase the voltage, the values of that delta remain the same or increase a little bit. But in this case, we can see that the values of the tan delta decreased as we increase the voltage. What happened in the phase L3 is that we have some water, and when we put some current in the cable during the tan delta test, some of that water dry it out, and for this reason we start to get lower values for the tan delta. Okay. Okay, talking of the connection setup for the tan delta test, in this case we're seeing our Vlf sinus 45 that has an internal tan delta. So the connection setup, it's very easy, very friendly. We have only our safety ground, the high voltage cable, and the power cord. Okay, very easy to connect this unit. And if we see the display of the unit, we will see the most important parameters during the test. We are seeing in this case the step voltages, the three step voltages, and the tan delta associated for each voltage step. Okay, we can see also the resistance, the measure of the resistance of the insulation. We can see the capacitance of the cable, of course, the frequency, etc., etc. Okay, and also once the test is done, we will get the result of the tan delta test. In this case, action required, a complete report with the important information in there. In this case, we are seeing only the phase L1, the graphic of the phase L1 and the result of L1, but of course we can have in one report the result for the three phases, okay? And of course, we will see the more important information as the average of the tan delta, the delta of the tan delta, and the standard deviation. For finish, I would like to talk about the Vlf units that we have at Megger. The first one I would like to talk is the Vlf Sinus 34. This unit has external tan delta attachment, and we use this Vlf for test cables up to 15 kV. And as I said, we have an external tan delta attachment, okay? And we can see it, the external tan delta. This is the smallest unit we have, the smallest Vlf unit we have in Megger. The next one is, before to go to the next one, of course, we have the option of buy the PDS62, that is a coupling capacitor, to measure and localize the partial discharge in the cable. So with this unit, we can do the three more important tests we do in cables: Vlf, tan delta, and partial discharge. The next unit we have is the Vlf Sinus 45 that we use to test to do the Vlf test in 15 kV and 25 kV cables. This unit has an internal 10 delta for the reason the connection is very easy. And of course, also we have the option of the coupling capacitor to measure the partial discharge and localize the partial discharge. And the last unit we have is the Vlf Sinus 62. This also has an internal 10 delta test. We use the unit to do a Vlf test in 15, 25, and 35 kV cables. And of course, also we have the PDS 62 coupling capacitor to measure partial discharge and do the localization of the partial discharge. Okay. So this is pretty much what I have for you guys. This is the last slide of my presentation, and I don't know, Michael, if you would like to add something.
Yeah, great job. Thanks for helping us out with that. At this time, the presentation portion of the webinar is officially concluded. We'll take about 30 minutes to answer as many of your questions as possible. If you have any questions, please submit them now into the Q&A box on the right side of your screen. For those of you that are leaving, when you close the webinar window, a survey should pop up on the screen. We would appreciate it greatly if you would take a few minutes of your time to provide feedback so we can continue to improve upon future webinars. On the survey, there's a field where you can also request a demo or a quote on any Megger products. A copy of the presentation, along with a link to the video recording of the webinar, will be emailed to everyone in about 2 business days, along with your credits, your PDH, and your CEUs. You can also view recordings of previous webinars on our website at us.megger.com/webinars and register for next month's webinar, Fundamentals of Partial Discharge Measurements. The presenter will be Charles Nybeck. So let's go over to your questions real quick. Our first one is going to be for Robert. For commissioning new cables, is VLF tan delta the first test you'd want to run, or would you say that power diagnostic is more meaningful?
Okay, so I hope I understood this correctly and everybody can hear me. So for commissioning new cables, as Javier pointed out, the 10 delta measures the aging condition of the cable. If you have a new cable, there is no aging, okay? And so the test is actually pretty ineffective on new cables. You will not measure anything. And what you measure, you expect that it is pretty low. And since the standard, as Javier also pointed out, has these traffic light, philosophy, it's also not really necessary to have any sort of fingerprint or whatever. So for a commissioning test, 10 delta is typically not necessary or not recommended. And we even see cases now where it is actually kind of confusing customers because, and Henning can comment on this much better than I do because he has a doctorate in chemistry, the cables still undergo changes in their insulation properties when they're new. So it is typically recommended not to touch the cable with 10 delta before it even reaches a year of age. So whatever you measure in this first few months to a year, or maybe a year and a half, depends, can be misleading. And then you might be in the situation that you do incorrect decision making because your 10 delta values are off. And we typically see with our customers, what we hear from them in our expert seminars, that most customers do not start 10 delta before 2 to 3 years at the very earliest. So many don't start before 5 years. And we had one case recently, which I would, credit as an extreme case. These guys have been burned by incorrect 10 delta assessments on new cables, and they have a working procedure that they don't measure 10 delta before the cable has not reached 7 years of age. And that is an extreme case, but it just illustrates the issue with the test. So the state of the art approach in the industry today is that when you do a commissioning test, which means you have to do a voltage withstand test and you should do some diagnostics, it is the partial discharge test that is the test that people are after. Because, if you don't have aging, the only thing that can go wrong is pretty much the splices, and the PD test is what reveals the issues and localizes the issues in the accessories. So that is the more recommended and the much more effective test. So VLF plus PD, 10 delta on new cables, not so much. And keep in mind what you're doing there.
Thanks, Robert. Our next question is going to be directed at Henning. With respect to blocking water penetration into Xlpe cables, can you please shed some light on comparing water barrier swelling tap, water barrier swelling powder, and lead sheaths?
All right. Well, now, like Javier was saying, the problem with basically both type of cables, solid dielectric and as well paper cables, is possible moisture ingress or water ingress into the cable. Now, on Xlpe cables or solid dielectric cables, also EPR cables, this can be, let's say, mitigated by putting either or both, one or two or both. You can put a special tape under the jacket, which basically, if the jacket gets punctured, would then absorb the moisture and not let it penetrate further into the cable. That is basically one prevention for getting moisture in. The other one is you can also put between the strands of the wire a material that would absorb water. And how does the water get between the strands? Well, this is unfortunate when many cables are installed and laying in the trench and they don't get capped off in time. There might be rain or moisture in the trench, and it gets sucked up between the strands of the conductor. And by putting this water block material in there, so that will not happen. So that's a way to on solid dielectric cables what can be done. On paper cables it's a little different. The biggest issue is on paper cables ingress of moisture, and the lead sheath, when it's a brand new sheath, is very effective of keeping moisture out. But the biggest problem with old paper cables is that the lead will develop stress cracks, longitudinal stress cracks, which are very hard to you cannot see with your naked eye. You need some special fluorescent methods to see the cracks. But even worse, most of paper cables, or many paper cables, are in duct. So you have no way of inspecting in the duct. So once these cracks form, then moisture can ingress through the cracks into the paper cable, and that is basically the end of the life of a paper cable. So I think that's what I can maybe mention about water ingress into cables.
Thanks. Robert, how can we estimate the remaining life of a cable?
Okay, that's a very interesting question. So first of all, to understand what's going on here a little bit, with the 10 delta, this standard or this guide that was made in IEEE, this 400.2, and by the way, Henning is also on the committee there. When you open up the standard and you look into the table and you see all these values, These values were established after a substantial study of a certain cable population was done. And this scientific base, so to speak, was delivered by or created by NETRAC. And first of all, NETRAC has a worksheet, a spreadsheet. I don't know exactly how to get it. I know, you probably have to contact them, but in this spreadsheet all the data of their tested population is available. So what you can do is on the first page you type in your name, and then on the second page you can type in your 10 delta values, and it will compare it against this population of test cables, so to speak. So that is one indication you can do. Also, if you really want to dig very deep, they also have a substantial comment on 10 delta as well on the background. And so the first thing how to estimate the remaining life is you have to get an idea how bad or how good your values are. And the standard is written, or the guide is written in a way that you can compare immediately your result without having to do any trending for 20 years before against these threshold values. And now, the tricky part is you will get, as Javier explained, this kind of traffic light system, okay? You will get no action required, further study advised, and action required. Now, as Javier also pointed out, action required does not necessarily mean the cable is completely bad and will fail the next day. Actually, to put a specific number on a result, because I guess this is what you're asking. You say, okay, I get these numbers. Will it fail in the next 3 years, or do I have 48 months or something like this? You cannot really do this, but you can know that your cable is in a non-critical condition, in a changing condition to the worse, or in a critical condition immediately. And then it's actually up to you to say, okay, do I repeat this measurement 6 months later to see if it got worse, or do I take any action? This is now more into the risk assessment part as well. How do you judge these values? How often do you retest? How risky is it to lose this cable? Because it is a big difference to get a bad result on a low priority cable compared to a high priority feeder cable, okay? So all of this plays into this, and this all affects how do you judge how much is really what I have left in the cable. What we know is if the values are really bad, it's much, much less, and failure will sooner or later happen. If it is very good, then you probably have a lot of life left. Another thing is, and Henning might comment on this as well, the type of insulation plays a big role. The first and second generation polyethylene was just terrible in terms of water treeing. Now, since you have the tree retardant Xlpe since the early 90s, the degree of treeing is much, much less. So the current, quality of Xlpe tree is about the same rate as the EPR, so very, very slow. So it takes a long time actually to see substantial problems. In the past, this was not the case, where the trees were really showing themselves a lot and early on.
Well, maybe. Oh, sorry. Continue.
No, let's Henning.
Maybe there's one brief comment on it. To really estimate remaining life is very difficult. And this is not semantics. What you can say is how much life you have lost up to the point. Because look at it this way: your life curve is a declining, let's say, exponential function, and for your dielectric properties. And if you do one test, you have 1 point on that life curve, so you don't know how you got there and where you got going from there. So if you had more points, then you can basically graph it out and get an idea where it would go. But from a practical point of view, if you have high 10 delta values, two things to that. Either you have really a very aged insulation, or, and that's always what people check out when they have high tan delta values, they check the terminations, because you can have a high tan delta value with a good insulation, but with a very poor termination, because you have leakage over the termination. So what people do on, let's say, expensive cables, expensive circuits, when they get high tan delta values, they will always first change the terminations and then retest it and see whether what they get for the true insulation. So, like I said, to estimate how much life is left is very difficult, but you can see where you stand on that life curve, and that gives you a good idea where, you know, how much more maybe you can expect from life. But it's not, there's no calculation you can do to do that.
All right. So Henny, since we have you on, our next question is directed at you.
Okay.
What is the ratio of increase the tan delta per year and the Xlpe type of insulation?
It ties right into what I just said. There is not a particular increase per year in the tan delta that is known, because it all depends on how quickly the aging will proceed in the cable insulation, and that depends on many circumstances. Okay, so there is no known value for this, because otherwise I would be right in the standard and tell you as an indicator, which would be great, but like I say, it's not possible, because we do not know what the aging characteristic and how quickly aging advances in a cable, and it can be very different. You know, you saw some three-phase cable diagrams, and many times what you see, one phase is different than the other two phases. So, you know, even the cable was installed at the same time, one phase has a different tan delta than the other two phases. So there is not such a per year increase that can be used. Maybe I can go on to the second question, to the other question here. Other cable test companies claim they can locate a corroded concentric neutral using a TDR signal. So yes, you can use a TDR signal, because what is a TDR signal measuring? You're measuring impedance change with the TDR. So you measure impedance change between conductor and neutral, and if the neutral is corroded, you will get a different impedance compared to when the neutral is a nice metallic neutral. The problem with this is that it's very subtle differences, and you have to use a very extremely high resolution TDR, which means you need an extremely narrow pulse width to measure this. And what that will do is you can only look very short distance with it. Typically, this method is used by the people who do cable injection, and they basically try to assess the condition of the neutral between splices. So normally the difference between splices, or the length difference, is maybe a couple hundred feet at the most. Okay, so that's where you can, with a scope, can see, but you cannot look for these changes in corrosion along a long cable. It's not possible. You can only do very short distances. So this is a big problem to really analyze the condition of the neutral. And you know, we're just working. I think it has been all finalized. There's a new or a revision of the IEEE standard about neutral corrosion, and that will give you some ideas about it. But there is really not a very simple, straightforward method to measure it on longer cables. Unfortunately not.
All right. Robert, is tan delta a worthwhile test for EPR cable? Does EPR cable fail by water treeing?
So the answer is yes and yes. You obviously you can do 10 delta on EPR cables. The guideline, the IEEE 400.2, has different tables for different insulation type cables. And yes, EPR cable does tree. That's actually known like for quite a while. There's papers on that, and it does tree. It is not free from water treeing. And just to give you a comparison, when you take the latest generation Xlpe, like the tree retardant stuff, which is also being refined by the manufacturers, as we see in the velocity. When you apply a radar, these values slightly go up, so that means the mixture gets, or the compound gets, also better and better. And this tree retardant Xlpe stuff is treeing at about the same rate as a good EPR insulation.
Thanks, Robert. Henning, how do you assess a hybrid circuit?
Well, I think Javier was alluding to that. Since we measure, the 10 delta measures dielectric properties of the insulation, and the dielectric properties of different type insulations, and most of the time is between when people have mixed cables like Xlpe spliced together with paper cables, the dielectric properties are very different. And they are different because one particular factor in the insulation, the permittivity, is very different. And so really, the values you get for 10 delta are very, very different. They are at a different absolute level. So when you have a mixed cable, and let's say you would have a cable where you have 90% Xlpe and 10% paper, you would measure basically the 10 delta of the paper, and because it's a high value, it might mask how good or how bad the Xlpe is. That's why it's not recommended to do this with 10 delta measurement. We work with some customers who have this. It's a very common situation in downtown networks where you have even maybe EPR, Xlpe, and paper cables in it. And this is really an application. If you want to do hyper testing or Vlf testing, then the cosine rectangular wave shape has a big advantage to offer here, because you can measure leakage current. Now, in leakage current, you have a similar issue because the leakage in paper is higher than the leakage in Xlpe. However, what you can do in these cables, and that's how it's done, you basically, the composition of this feeder or this cable, you run a Vlf test including the leakage current, and you fingerprint it. You say, okay, now I know this in this configuration, this cable has so much leakage current. When you run it again and you didn't change the configuration, maybe in 2 years, and you look at the leakage current, if the leakage current has increased, then obviously it's going not to the better. And companies record these leakage currents so they can see the trend of the insulation. Now, if you would change in such a cable, let's say and that happens quite often, people replacing paper sections with Xlpe, so that changes obviously the whole leakage current for the feeder. So you have to reestablish the leakage current number for that particular feeder after you do a major, let's say, cable exchange. Okay, so, but it's not a very a straightforward solution to it. You need some experience, and the experience comes from the historic data you have on these cables.
All right, thanks. Javier, when testing a 15 kV cable, what are the 3 values of U0 to be used, and what exactly is U0?
Okay, U0 is the operation voltage between the conductor and the concentric. So when we talk of 15 kV cables, Normally or typically the operation voltage will be 13.8. In that case, the U naught will be equal to 8 kV. In this case, then 0.5 U naught will be equal to 4 kV. 1 U naught will be 8, as I said, and 1.5 U naught will be equal to 12 kV.
All right, thanks. Robert, can you explain why cosine waveform cannot be used for testing?
Yes. So, well, it can be used for testing, just not for 10 delta. So as Henning already explained, with the cosine rectangular waveform, you have an advantage that you are able to measure leakage current. You cannot measure leakage current with the sinusoidal wave because there is no leakage current defined. At any point of the curve, you have a different gradient, so you cannot define this. And please don't confuse these current numbers on any machine that the machine shows you. That is total charging current. That is not the leakage current. And so the problem with the cosine rectangular waveform for 10 delta is that it is a near power frequency waveform when you change polarity. So it has the same slope as a 50 or 60 hertz power frequency or line frequency voltage. But then you have the DC plateau-like phase. So you swing over at a very steep slope, which is nice for PD measurement, and then you keep the voltage up, and then you reverse polarity again. And in this last second, you typically, before it swings over again, you measure leakage current. But as Javier explained, the phase shift between the voltage and the current is for this property is only defined with a sinusoidal waveform. So if you have this shaped rectangular waveform, this cosine rectangular waveform, this is not defined in the same way as it is for the sinusoidal wave. So it's kind of exclusive. If you want to measure leakage current, you need the cosine rectangular waveform. If you need to measure 10 delta, you need a sinusoidal output on your test set as well.
All right, excellent. Henning, what should be the test step duration, and how long do you hold on to the voltage for each step?
Well, the test step duration is defined by the number of test points you will set up for each test voltage. And typically, you want to have at least 5 test points per voltage step. Now, each test point now has to be long enough to get a steady reading. So typically, you can say maybe 20, 30 seconds should be typically enough time to get a steady reading per test point. So if you have 5 test points, you can say 5 times 30 seconds. It's basically about 2.5 minutes per test point, per voltage step. And then you do this for all 3 voltage points, right? So there is not a mandatory requirement. Some people use 10 test points. Like Javier was saying, when you do the standard deviation, obviously the more test points you have, the better the standard deviation can be calculated for that voltage. So.
All right. While we have you, why does rain affect TD results if the water is not entering the cable? Does water or weather conditions affect measurements of underground cables and conduits?
Well, there are two questions in one here, right? One is basically how rain affects it, and rain can only affect an underground cable wherever you have a termination. So if you have in an open substation, which is typically the case, if you have terminations that are exposed to the environment, and you have isolated the termination, which you must, because you must test a isolated cable, Then, if you have rain, then obviously you have moisture and you can get leakage over the termination, which will affect your reading. This is no different than when you did in the old days a DC hyper test where you measured leakage current. People always say when it was really humid and moist, they had higher readings because you have creepage over or leakage over the termination. So the only thing you can do there is you have to really clean the terminations, and you have to wipe them dry, and do that. Now, in the conduit, if you have water in the conduit, now that's a different issue. That comes right back to measuring basically if you had water ingress or moisture ingress into the cable insulation. Now you measure it in the insulation. That means that water is really in the insulation, and it's a bad thing. Where when it's on the termination, you typically have a way to circumvent that or to mitigate it. Okay.
All right, and the next question for you is: in transformers, we usually use guard rings to college the leak in current in the bushings. What about in the cables?
Yeah. Well, theoretically, a 10 delta measurement should be always done with guard rings. Okay, that is, from the theory, the best possible measurement you can do. But there are some practical considerations you have to do. First of all, there is and we even offer this, so you can apply guard rings and to do a 10 delta measurement. However, what you need to have is at least 2 phases or 3 phases, because what you do is you basically take the leakage current over the termination that you don't want to affect your reading, your 10 delta reading, because it has nothing to do with the insulation condition. And you take that and you basically divert it over the second phase back to your measurement device. So you have 2 currents and you can subtract the 2 currents, and that allows you to measure the true, let's say, dielectric loss in the insulation of the first phase. So it's possible to do that, but I have to be honest with you, I have not seen any customer doing that. The biggest issue is keep the terminations clean and do your test, because it normally is sufficient for this. The guard ring technology for 10 delta is can be done, but it's much more involved.
All right, Javier, is there a minimum and maximum cable lengths to perform VLF and TD tests?
Okay, well, regarding the minimum, maybe 82 feet will be the minimum length of cable, because it not makes sense to do a 10 delta test in a shorter cable. Okay, I can change the cable and that's it. Okay. Regarding the length of the maximum length of the cable, it will depend of the capacitance of the cable. Okay, normally the VLF sinus, have around one microfarad of capacitance, of test capacitance, and the cables depends of the voltage and the size of the conductor. But we could say that per kilometer we have around between more or less 0.3 microfarads. Okay, so I will say that maybe we can test at 0.1 hertz up to 3 kilometers, or maybe a little more. The option that we have when we have a very, very long cable, let's say that we are talking of very, very long cable, we can decrease the frequency to do the 10 delta test. But the problem that we will have is that we will not compare our results with the tables in the IEEE 400.2. So the only that we can do with that result is do some comparison between the phases if we decrease the frequency during the 10 delta test. Okay, So answering the question, I will say that maybe the shorter will be 82 feet, and maybe, sorry, I don't know the number in feet, but I will say maybe 3-4 kilometers could be the longest at 0.1 hertz.
Let me,
Thank
can I
you.
add something to you to that real quickly, just briefly?
Absolutely.
Just keep in mind, Javier's right, the sinusoidal test units are typically much lower test capacitance, in terms of what you can do with it compared to the cosine rectangular. But for the 10 delta, you also don't go typically to the maximum output of the machine, because all of these machines, if you look into the data sheets, this 1 microfarad is also at maximum output at 0.1 hertz. So as we saw, you do the test at 0.5, at 1 U0, and at 1.5. Now, that means you don't go even remotely as high as on the VLF withstand tests with the machine. And that also helps that you, with 10 delta, can handle cables with, you can do 10 delta on cables, where if you would just try to do a straight VLF test, you could not handle them. So you have a little bit of wiggle room there, because the 10 delta is in terms of stress below the withstand test in terms of how high you go with the voltage. And that also helps because the machines have a load curve, right? And if you go down in voltage compared to the maximum what the machine can do, you also gain a few percent on test capacitance.
Thanks for adding that. It was real great. So the next question is for Henning. In the IEEE standard, it talks about mineral-filled EPR. Is there a way to know if your EPR cable is or is not filled with mineral or mineral-filled?
Well, that is really the difference between Xlpe and EPR cable. EPR is a copolymer, but it's also filled always with mineral fillers. And so there is no EPR cable without mineral fillers. So any EPR cable has mineral fillers. And that's also the reason, because you have different cable manufacturers use different formulations of the copolymer and also the amount of filler they put in. That's why, in contrast to Xlpe, where Xlpe is let's say a unique compound that, regardless of the height of the finished cable, Xlpe has the same properties. But on EPR, it depends very much on the manufacturer what the exact dielectric properties of the cable are. And like I said, EPR is always mineral filled.
All right. Is tan delta a good test on PILC cable with 3 conductors on a single cable?
Well, yeah, you have to differentiate a little bit, because you can have 2 types of, let's say, 3-core paper cables. The older type of 3-core paper cables is called a belted cable, where the phases are insulated, but they have one common neutral, and so each phase doesn't have its own neutral. So compared to the newer paper cables, where each of the 3 cores has its insulation and each of the 3 cores has its own neutral. Why that makes a difference? Because you measure dielectric properties, and you always have to measure dielectric properties between conductor and shield. So in the first case, when you have a belted cable, you can really not measure individual cables, or individual phases, I should say. You can measure the whole thing and see what the losses are, but you cannot measure the individual phase. Where in the second situation, where you have individual neutrals on each core or phase, you can do that. So many times, however, what the real issue is that when you have a circuit, a paper insulated circuit, you many times have old and new mixed together. So you have belted and non-belted cable in the same circuit. And the only thing you can measure then is the total dielectric loss in this cable, because you cannot differentiate. You have no access to, unless you can sectionalize each section, but that will be, something totally unpractical, because you will have to cut all the splices open. So the answer is you can measure it, but for, depending on what type of paper cable you have to be aware of what you're measuring, total losses or individual losses.
All right. The next question is also for you. Is corona or PD not an issue with 4160 voltage systems?
Let me see here. I just have to advance my screen. Well, corona or PD, what is it? This is a gas discharge in a pocket or in a void or on a surface between 2 points of different potential, where the voltage is high enough, the electrical field is high enough to break down the air or the gas in the gap. So it can happen on 4160. I mean, look at it this way. I can draw an arc when I remove a plug from a 120 volt outlet, right? I can draw an arc if I want to. So that means the voltage is only 120 volts. How can I draw an arc? Because the gap is so small and the voltage is high enough to make the air break down. So the answer to that question is sure, you can have also on 4160 systems, which are probably typically motor systems. You can have also corona or PD.
All right.
Okay.
Robert. Yeah, that was great. Robert, what is the interval to conduct the Vlf TD and PD testing for an aged cable?
Okay, so there is no fixed interval for this. And as Henning pointed out, this has very much to do with, where are you at on the life curve, the bathtub curve, because a cable is an asset like a transformer or anything else. So you can say it has a life curve. On top of that, there's an asset management view on this as well, because you want to do the testing as much as necessary and as little as you can get away with. So it makes sense, because everybody wants to optimize where to put the money and how much money to spend. Now, on a serviced age cable, if you really have water treeing, the test that brings that out, first of all, to know it would be the 10 delta test, and then to have the go no go, that the insulation is still good for a certain amount of time. That is done with the Vlf test. Now, again, think about other, factors that you have to take into consideration, like how important is the cable. You will answer this question differently for an important feeder cable versus a not so important cable that runs somewhere where simply there's no crucial customer, where there's no high density of population and all of these things. And actually, to give you an example, most of the German utilities, for their assessment mainly of the PD values, the PD testing results, they use by experience, and it took them a while to get there, but by experience and exchange between each other and publication and databases on failures, they typically, all of them, use some variation of a matrix where they pretty much order their assets by priority, or how, let's say, how much impact would it have to lose that cable? How important is it? How difficult is it to replace? That's another thing. And that is one of the determining factors on how often would they retest, and how fast would they have to act if something happens, or if they find a condition that they're not happy with. So the interval varies. So for the Vlf test, for instance, I mean, there is statistic evidence brought on the table by two major international standards. If you do a Vlf test with the right test parameters, then you will have no problems with water tree induced aging or failures for 2 to 3 years when you pass the test. Because if you would have a critical sized water tree, as Javier showed in the presentation, I repeat, a properly conducted Vlf test will rake these imminent failures out of your system. So for the Vlf test, you say, 3 years, for instance. Some people do 5 years. Also, that depends. On the Tandelta, same thing. It depends on the results. If you have a cable that is already service aged, but it has very good results, and it might not be an important cable, you test less frequently than if it is an important cable. And the same goes for the PD testing. So it really depends. And maybe Henning has to add to this, but if the condition gets worse and worse and worse, you would test more often. And sometimes even seasonal things have to be taken into account. We had customers, they had problems in spring, and then they repeated the measurement and they got different results in summer because they had a cable or an acid in an extreme environment that was very weather sensitive. And again, important feeder cables naturally more often because it would be a much higher impact to lose those cables. So it really depends on the results and on the asset overall.
All right. Next question is for you. Can tan delta be done on a long cable where there's a splice or is connected to a junction box?
Is that for me as well? Yes. Yes, it can be done. However, as Javier also explained, the problem here is that the tan delta is defined for 0.1 hertz. There is no reference values, no tables. If you allow the test set to reduce the frequency, which you should not, neither for the VLF nor for the tan delta, if you really do this, you're on your own. Nobody in the world can help you and say, oh, hey, let me share my values for 0.01 hertz. The test or the guide is really defined for 0.1 hertz, and this is the only frequency where these values can be used to compare against. And as Javier explained, the next best thing would be, the only thing I can do then, if I do this, I can only compare the phases of the same cable which I tested in the same way. Now, similar with terminations, splices typically do not have that much of an influence as long as they are okay. And junction boxes also, it depends. You could have more leakage and also a little bit of influence on the tan delta there, but it really depends. Now, if the splice is really, really bad, it will have an influence. If the junction box is in a really, really bad condition, think about surface leakage, then it's the same as with a termination. If internally you have additional paths on surfaces where you can have additional creepage, then the tan delta value is always influenced. Or as Javier showed in the example, water. A splice can have an influence if it's full of water, because then you see these that the tip off suddenly stops or goes flat from 1 to 1.5, or it goes negative. That's a typical indication of local moisture somewhere in the cable. And these junction boxes, they can also, be full of water. If it rained and, it just fills up as you have it sometimes, then you could also under certain circumstances have influences there.
Maybe I can add a little bit to this. Whenever you do a test, it doesn't matter what type of test, you should try to do it under the best possible circumstances. And when you trying to measure the dielectric losses of a cable, the best way is to have an isolated cable. And that means the splice you cannot isolate. The splice is part of your cable system. But the junction box is typically something you do not want to leave in a circuit when you do dielectric testing. So you typically want to disconnect at the junction box. Say if it's like also if you have a switch, you can open a switch and still have the termination bolted onto the open side of the switch. But that open side of the switch, like Robert was saying, still has some surfaces and is somewhere connected to ground. So you always set yourself up to create a leakage path or a creepage path. And that's why the best advice is to really remove from any type of, the terminations, to really remove the terminations. And in some cases, even, if you get still strange results, to remove the termination, okay? Like if you had an elbow attached to it, okay? By the way, that's an important aspect. People pull an elbow off and do a Vlf test, and they suddenly go on a 15 kV cable. You go with maybe, what is the voltage now? 30 kV, right, for testing, for if you do a hypo test. So you have to watch, because you can get inside the elbow, the typical load break elbow, you can get flashover. So you might have to typically what you do in that situation, you put a plug into the elbow to eliminate the air gap inside the elbow. Otherwise, you might have problems. We had seen this in, actually, Javier, remember we did some testing in Mexico somewhere, and that was a problem. They went to about 40 kV, and we had all kind of problems. Yeah. And that was because the elbows would flash over. So, sometimes you might have to remove the elbow. I mean, I'm not saying you must do this, but you should do it as best as you can, especially when you get very suspicious readings. Then you have to make sure where is it coming from. And there you have to maybe take extra care and extra precautions when you do this type of testing, so you don't fall in the trap and misinterpret the results.
Thanks, Henning, and thank you, Robert and Javier. It looks like that's all the time we have for questions. I apologize if we didn't get to your question today, but we will follow up with you offline the next couple weeks after the holiday break. With that being said, thank you all for attending. If you could please remember to answer the survey. This survey also includes a field for you to request a quote or a demo if you're interested. Thank you all again for attending, and have a great holiday break.
Thank you.
Thank you.
Thank you. Bye-bye.
Bye-bye.
Bye-bye.